We want to relate what we learned in lab on Monday to the sine curves we learned later in the week. We want to start by trying to track a pendulum. So if we have a game like Pitfall and we want to model nature and figure out where our object is going to be at each moment in time, we need to be able to figure out the math of pendulum motion. So to do this in lab, what we did is we started with our pocket lab and we lined it up with the baseball when the baseball was hanging straight down. That distance from the pocket lab to the ball when it's at equilibrium, we call D. That distance turns out to be the vertical shift of our sine curve. We then take the ball, we move it closer to the pocket lab and let it go. We see the ball moving away from its starting point, passing the equilibrium point, and going to its other extreme spot. We then see it moving back again toward where it started. This repetitive motion will create a sine curve. The sine curve is not necessarily a perfect sine curve because in this case, we started at the closest position. We hit collect when the ball was really close to the pocket lab. So when we trace this out, we get a sine curve, but technically it is a negative cosine curve, or a sine curve with a phase shift of 3 pi over 2. We'd like to know how this sine curve looks mathematically. So we already learned that the D is how far it was from the pocket lab to the ball when the ball is hanging straight down. A is how far back we pull the ball. It's the amplitude. It's the distance from right in the middle to its farthest spot in either direction. We control both the D and the A. The C is determined solely by when we hit collect. We hit collect when it was really close to the pocket lab, so we got a C value of 3 pi over 2. The important thing to realize is that A and C and D are all controlled by us. The most important variable is B, and that is controlled by nature. We learned that B can be found by doing 2 pi times the frequency or 2 pi divided by the period. So we just have to figure out, how do you figure out the period or the frequency of a pendulum? Again, we don't control that, nature does. So when we plotted this thing out, we collected our data and we tried to figure out relationships. Hopefully you remember that when we did this, angle had no effect on period. Mass had no effect on period. The reason why angle doesn't matter is because if you pull it back a tiny angle, it'll swing really slowly and take a certain amount of time to go back and forth. If you pull it back farther, it goes a bigger distance, but it goes faster. Those two factors cancel out and you get no relationship. With mass, it turns out that small masses and big masses fall at the exact same rate. So just like free fall, the pendulum is controlled by gravity and mass does not affect that. This G is the gravitational field on Earth or the acceleration due to gravity on Earth, and that would be 9.8. This length is the length measured in meters. We saw that this square root sign was because we had a square root relationship for length and we had an inverse square root relationship for gravitational field. Some of you tried to do a linear graph, and although the points fit, it should be obvious that we have to go through 0, 0. A pendulum with no length would also have no period. I'm going to ask you to try to do a couple math problems. First, I'd like you to find if you have a pendulum with a length of 1 meter. Notice you measure from your pivot point to the center of the object. I'd like you to find the period and the frequency. So you know from today the period formula, and you know from before the frequency formula. So plug 1 meter in as your length, 9.8 as your gravity, and solve for T. Once you have T, put it in here and solve for frequency. You should pause now and work through this. Here is what you should have found. I'd now like you to try going backwards. So we made a pendulum out by the football field, and I'd like to see if you could figure out the length of the pendulum, even though you can't see the entire string. Okay, so we release the pendulum, we allow it to swing a few times, and we time it. 2 swings took 9.174 seconds. So what we want to do is use our formula for period. The period is not this time, because that's for 2 swings. You want to divide it by the number of swings. So in this case, 2. Divide, put it in as the period, solve for length. Again, you can call this gravitational field, or you can call it acceleration due to gravity. Either way, use 9.8. This algebra is tricky, so try to pause, work through it, and see if you get the proper length. Again, this 4.57 is half of the 9.174. You divide that by 2 pi. Be very careful in your calculator. Put the 2 pi in parentheses, or alternatively just call it 6.28. Either way, make sure when you divide, you get 0.73. This is the number one place you're going to make your mistake. So make sure you do this properly. I'd like you to try 2 now where I'm not going to help you. 1 is Hannah swinging in the auxiliary gym.
Oh my God.
We're going to have her swing back and forth, and we're going to time her.
That's for physics, Aiden!
And you never just count 1 oscillation. Your results will be way too inaccurate.
Oh my
So we're
God.
going to let her swing 5
I
times.
think we're good.
And when we do that, we find that it took 18.46 seconds. So 5 oscillations in 18.46 seconds. Find her period, her frequency, how many oscillations she makes in a minute, and find the length of the pendulum. Remember that frequency is oscillations per second. So all you have to do is convert seconds into minutes to find oscillations per minute. The final problem you're going to do is take the Franklin Institute pendulum. I tell you its length. Just work directly, find the period, find the frequency, find out how many oscillations it makes per minute. Good luck. Please reach out to me if you have any questions.